Hello, everybody. Good morning, good evening, good afternoon, wherever you are. This is the XC22 session on evaluation and performance. I'm Max Di Penta, session chair of this session. We have 4 papers in this session, and now we are going to listen the short presentation for those papers, and after that, we will have a discussion slot. So for the audience and also for the authors, if you have questions, you can either start to write your questions in the chat or keep the question for later and then just after you open the mic and ask questions by voice. So we start with the first presentation. The first presentation is going to be given by Christoph Leber, and this is a journal first paper titled Predicting Stable Software Benchmarks Using Static Source Code Features. Please. Okay, I guess you are muted, Christoph.
Yeah, do you want to unmute yourself?
Sorry, I had some troubles with my headphones. And suddenly I couldn't hear you anymore.
Okay.
We can hear you.
That's good. Very well. So I thought, I suppose that I have to start. I couldn't hear anything, but yeah. Okay. Hi, everybody. Today I'm going to talk about our MZ paper, journal first paper at ICSI, which is called Predicting Unstable Software Benchmarks Using Static Source Code Features. My name is Christoph Laber. I'm a postdoc at Similar Research Lab. So in this paper, we focused on a particular performance testing technique, which is called software microbenchmarks. They are somewhat equivalent to what unit tests are for functional testing, but for performance. So they are similarly defined in source code, where you just write a function or a method that invokes whatever you want to benchmark. And then the benchmarking harness takes this method and executes it for many iterations, for many repeated iterations to get reliable results. And for each of this iteration, the harness measures the execution time, for example. So what we get as a result then of our benchmark execution is a distribution of values. And this is different from unit tests, where we only have a binary answer, pass or fail. In benchmarks, we have a distribution of values that we need to compare to different versions or to different implementations of an algorithm. The challenge that we focused on in this paper is the variability among the results of a benchmark and how we can tackle this variability problem. So in simple terms, we basically have 2 scenarios. On one side, we can have a benchmark with low variability, and on the other side, we can have a benchmark with high variability amongst its results. And this can have different implications. So when we have a benchmark with low variability, we can be sure that it has reliable performance change detection capabilities. That means whenever we detect a change, we can be sure it's a true positive. However, if we have high variability, we can potentially have one of these 2 scenarios where we detect a change, although there shouldn't be one, so a false positive, or we do not detect the change because the performance change is masked by the variability of the results, so a false negative. But it's really hard to say whether a benchmark will have low or high variability. Only after we have executed it, it becomes evident, and when we look at the results. And it's always bound to a specific execution environment where we execute the benchmarks in. So, for example, it might be very stable in a performance testing environment, but it might be very unstable on the developer machine. What we can do is, well, we can only execute as many of these repeated iterations, so as many as necessary, whatever that means, to get stable results. The idea in our paper, however, is to take the benchmark in its representation in source code, feed it into a machine learning model, in particular a binary classification model, that was trained on executions from other benchmarks in a particular environment. And this model then tells us whether this benchmark, represented by its source code, is going to be stable or unstable in that environment without the need to execute it. For this, we propose our instability prediction approach. And here we, imagine we have a benchmark, we construct a static call graph from this benchmark, and which gives us the set of reachable functions. So, and then for each of these reachable functions and the benchmark itself, we parse the AST and extract certain features. In total, we extract 58 different features related to meta information, programming language features, and standard library API calls. And the main idea here is to extract features that can serve as proxies for performance variability. And all these features are influenced by previous research. So what we then have is we have a set of features related to the benchmark code itself, and we combine the feature counts of all the functions that are reachable by the benchmark. So this is like the code feature set that we have. We feed these two feature sets into the machine learning model, which then tells us whether the benchmark is going to be stable or unstable. We evaluated this approach on over 4,000 individual Go benchmarks, computed or extracted the static source code features for each of the benchmarks, and computed the stability or instability of each of these benchmarks in a very dedicated environment. And we do this for a different number of iterations for which the benchmark was executed for, as well as for different threshold of what we consider to be stable or unstable. We then train multiple models based on 11 different machine learning algorithms to answer our research question. The first one is about whether we can even predict it and what the prediction performance is. And the other one is about the importance of individual features as well as categories of features. What we find is that, yes, we can actually predict performance based on the static features. And the best prediction performance is at 0.90 area under the curve and 0.61 Matthews correlation coefficient if we train the model on the highest threshold and the most iterations and use random forest for it. In terms of the feature importance, we find that only 7 of the 58 different features are individually important, but collectively all code features are important for good predictions. With that, I thank you for listening and encourage you to read the paper, which is openly available, and watch the longer talk, which is on YouTube. Thank you.
Thanks a lot. So we'll keep the question for later, but everybody feel free to start writing questions. Now we move to the second paper. The second paper is a software engineering education and training paper. It's going to be presented by Daria Bogdanova, and the title of the paper is Academic and Industry Training for Data Modeling, Ideas and Mutual Benefit. Please, Daria.
Yeah, thank you. Just one moment, let me share my screen. Okay, so yes, I'm presenting academic and industry training for data modeling, ideas for mutual benefit. It is less of a technical paper, but more of a conceptual paper and idea paper for ideas exchanged between the industry, which I represent. I work at Sitecore as a technical trainer, and the academia, and my second author is from University of Leuven in Belgium. So academic and industry training and industry and academia are commonly viewed as entirely different worlds when it comes to software engineering education. University level software engineering programs, they often fail to provide the students with the skills necessary for their industry jobs. I think many of you know about this problem. And there were multiple studies regarding the desired knowledge and skills in the industry and what is given in the academia, but actually hardly anyone explores the knowledge gap between academia and industry and whether it is closed by industry training. So the academia and industry, of course, have certain differences in approaches to education, difference in desired and covered skills, because academia has their own learning outcomes, learning goals, and industry has their own. And overall, we experience lack of communication between industry and academia. Can we safely assume that industry training successfully covers the knowledge gap? The onboarding, all the practical tasks that people do in their jobs when they join the industry probably should be able to cover this gap. But actually, yeah, so intuitively, the answer is yes. the actual answer is no. Even though professionals are more experienced and they still make the same mistakes the students make. In the field, particularly of conceptual data modeling, which is my field, errors that are made by students, they are studied extensively because, yeah, it's easier to access, of course, access the student data. Errors made by professionals, nobody knows what they are. And that's something that we want to explore a little bit more. So we explored 2 courses on conceptual data modeling, master level course and industry professional training at site core. And these are just the different parameters of these courses. So short-term versus long-term, etc., etc., etc. So both of them are implemented in the sandbox, so students can have the practice, and the target role of the students is clearly known, of course, for industrial specialists and vaguely known for academics. We did a requirements analysis, conceptual data model, draft design, behavioral model design. The preliminary findings show that in the academic training, most challenging topic is requirements analysis, most common errors, association multiplicity errors, and wrong direction of association. So this is the type of errors that we get. Those of you who know the UML, they will understand right away what we mean. And in the industry training, which is very surprising, the most challenging topic is still the same. The most common errors are still the same, even with seasoned professionals. So this shows that actually those things that are not covered in the academia, they keep having returned afterwards in the industry as well. So it's exactly the same common error. So that's something that we are going to explore further. And we have some proposed direction. We want to introduce error identification and classification with an error classification framework. We want to find overlaps between the industry and academia-based errors. Develop the treatment and find better ways to teach, evaluate the treatments in both target groups. And finally, we would like to do some methodology exchange using blending and academic and industry style training for conceptual data modeling. So, yeah, thank you. That's it.
Thanks a lot. Okay. So now we have a technical track paper, and we move from models to actual code, Python code. This paper is going to be presented by Wei Cheng, and the paper is about conflict-aware inference of Python-compatible runtime environments with domain knowledge graphs. Please.
Okay, thank you. Hello, everyone. My name is Chen Wei from Nanjing University. I'm going to present our work, Conflict-Aware Inference of Python-Compatible Runtime Environments with Domain Knowledge Graph. In this task, given a single field Python code snippet, we need to infer a list of Python packages with specific versions and the Python version to generate the compatible runtime environment. It can contribute to code sharing and the reuse of Python code and automated software configuration management. This is an overview of our approach, PyCRE. The upper portion of the figure shows the construction of our Python package knowledge graph, which maintains a great deal of domain knowledge. And the bottom portion shows the automatic inference of compatible runtime environments. We design an ontology for Python third-party package to represent the relationships between the entities in real world. New to our work is the submodel, attributes node, and the requires age, which indicates the direct dependencies of the versions. To serialize the only input, we fully pass the target code into an abstract syntax tree and work for the imported models and the code attributes. And the results of code parsing can be used to infer the Python versions. We define a matching degree based on the longest prefix match of the reference space. And for each parse tree, we calculate the matching degree for models and attributes in order to discover the candidate libraries. We propose an heuristic graph transformer algorithm for dependency solving. It has two heuristic strategies. One is priority. We perform the latest compatible version. And the other is pruning. If one version of a package is incompatible, we skip the other versions with identical version specifications. And we use a set solver as the fallback for the completeness. For the fairness of our experiments, our method should acquire knowledge for the same Python packages. There are over 10 million entities and over 100 million relationships in our knowledge graph. As shown in the table, our PyCRE is significantly better than the comparative methods in all three different settings. And even with more complex process, the inference time of PyCRE is still short and comparable. In conclusion, we design a domain-specific ontology for Python third-party packages and an automatic approach to constructing the knowledge graph. And we define a new metric of matching degree between Python libraries and third-party resources and propose an efficient heuristic algorithm for dependency solving. Other details are shown in our paper. Thanks for listening.
Thank you very much. Okay, so now we can move to the last paper again. That's a technical track paper, and it's going to be presented by Peter Garam-Vogli. And the title of the paper is Utilizing Parallelism in Smart Contracts on Decentralized Blockchain by Taming Application Inherent Conflicts.
Thank you, Matt. Sorry for the complicated name. Hey everyone, my name is Peter, and today I'll be presenting to you our work on parallel execution of blockchain transactions. So on blockchains, usually consensus, network, storage, and execution might all become performance bottlenecks. Recent work has addressed the consensus as the bottleneck, and we argue that execution is the hardest one to solve because Ethereum and similar blockchains execute transactions serially. So in this work, our goal is to speed up execution through parallelism, ideally without fundamentally changing the protocol. So in our work, we found two main problems. The first one is that it seems that existing blockchain datasets or transaction workloads seem to be severely bottlenecked. So we ran a simulation, a historical dataset, and we found that the best case speedup that we could achieve was 4 times compared to serial execution, even if we used 8 or 16 threads. And this is because many blocks are bottlenecked on a series of dependent or conflicting transactions. These usually belong to applications like token transfers, decentralized finance, and games and collectibles. And if we trace it back to the programming construct responsible for the conflict, it's usually counters or arrays. So we want to propose some techniques to eliminate these bottlenecks. And the main idea is that if you have a chain of transactions that are dependent on each other, what we want to do is remove some dependencies so that cut this chain into multiple independent chains that can be run in parallel. So for instance, for token distributions, which is when from a single sender address, you send many transactions to many receivers, the sender balance can become the source of contention or conflict. We propose conflict-aware token distribution, which means simply to use 2 or more sender addresses instead of just one. Very different sender address transactions can be viewed as independent from each other. A more general approach is, which is that one counter, let's say an integer, is, so it looks like an integer, but under the hood, it's actually consisting of multiple storage locations or multiple variables. This way, if you have concurrent transactions modifying the same counter, they might work on different variables, and this way we can avoid conflict. And finally, we also point out that many operations are semantically commutative, but this cannot be expressed in the Ethereum virtual machine. So commutative transactions like counter increments will still conflict. So we propose to introduce some new instructions to the virtual machine to express this commutativity and allow such transactions to be concurrently executed. Our evaluations suggest that assuming that these techniques can be applied to a majority of conflicts, they drastically increase the parallelizability of the transaction dataset. The second problem that we point out is that of non-determinism. So in blockchain systems, determinism is very important because independent nodes need to be able to execute the same transaction dataset or transaction workload and reach the same result so that they can reach consensus. But with parallel execution, this is not always the case. Let us look at, let's assume that transaction 3 depends on transaction 1. So on node A, they're executed in this order, 1, 3. So 3 can be committed because it sees all the updates by 1. But let's assume that on node B, the different order, 3, 1. So this way, the scheduler will detect the conflict and it has to abort 3. So you see that transaction 3 is committed on node A, but it's aborted and re-executed on node B. And this kind of inconsistency in a blockchain setting might actually cause the replicated state machine to diverge on the two nodes. We propose to solve this by a new scheduling algorithm called optimistic concurrency control with deterministic aborts, or OCCDA for short. And the idea is very simple. On node A, transaction 3 could be committed because it sees all the updates, but we forcibly abort it and re-execute it. Furthermore, this abort will be made prior to the execution of the transactions so that it can be done uniformly across all the nodes. This way, we can ensure that all the nodes in the distributed network, the distributed blockchain network, we reach the same abort commit decisions and we can reach consistency and consensus. We expect some performance impact from this approach because transactions that could be committed need to be aborted. But based on our evaluations, the performance impact seems to be well within the acceptable range. So to summarize our work, our goal is to work towards parallel execution of blockchain transactions. And we pointed out two issues. One is bottleneck dependencies, and the other one is non-determinism. In our paper, we proposed some approaches how to solve these issues, and we hope to unlock further research towards parallel execution of blockchain transactions. Thank you.
Okay, thank you very much. All right, now the floor is open for questions. Please. Any question from the audience or from the speakers to other speakers? So we have a first question from Feng Li to Wei. And the question is, what does query the knowledge graph to obtain spanning tree mean?
Okay. Please wait a minute.
Sure.
Okay. At first, the root node of the path tree is the top level model, and we will query the knowledge graph started at the top level model. Two is sub models and attributes to form a tree, which is the spanning tree.
Okay.
It's all. Thank you.
Okay, thank you. Other questions, comments? Not
Yeah,
yet.
maybe I can
Yes.
follow up for
Yes, please,
for
please,
me.
please.
So I find it interesting that that you went through like the typical way of version selection, always picking the highest version or the most so the newest version possible. And like a different approach is what the Go language did, for example, in their module and version and package management system. They picked the minimally applicable version and thereby the minimally version that is possible for all the packages, but to still get like a coherent set. And they reduced the complexity from MP to NL. So I was wondering whether you are aware of that, and yeah, and what do you think basically? Because by that they can remove they can remove the reliability on set solving.
Do you mean the version of the package?
Yeah.
Okay. We select the our algorithm has the heuristic strategies, because we think the new version have more API or have more APIs than the older one, and in most cases the new version is compatible with the older one.
All right.
Just a follow-up. In how many cases you found that newer version break compatibility?
Sorry?
Yeah, my question is to what extent newer versions could break compatibilities, because it's not guaranteed that a new version of library are still compatible with older code.
It seems the network is not good.
Okay.
Max, maybe you could put your question in the chat room.
Yeah. Oh, the network, you mean? Okay, you cannot hear me. So.
The answer is yes in some cases. The newer version may introduce the new version constraints for the other packages. It may cause the incompatibility.
Okay. Thank you. All right. Other questions? Otherwise, I will go ahead and start questions also to some other speaker, and then I have some follow-up for Wei as well. Okay, maybe.
If the audience
yes.
doesn't have a question, I would have a question to Christoph.
Yes.
Thank you for
please.
the great presentation. I find your conclusion pleasantly surprising that the predictability is so good. And you mentioned that 7 out of 58 features seem to be the most important. I was wondering if you could maybe give an example of what kind of features predict this very well.
Sure. I got the exact same question yesterday, so I came already prepared. So 4 out of these 7 features relate to the benchmark code itself. And 3 out of those 4 are more, let's say, meta features, lines of code of the benchmark. lines of code in the file where the benchmark was created, a number of files in the package, but also nested loops within the benchmark. And the other 3 of the 7 are related to the code that the benchmark calls. And here again, we have nested loops, dynamic arrays, or the usage of dynamic arrays, as well as API calls to synchronization packages. So something like mutexes or weight groups, etc. However, this, and we discussed this in the paper, just because we only found 7 of these features to be individually important, I always like to stress that they are individually important. We looked at permutation feature importance, which basically randomly changes the values of individual features and then looks at how the prediction performance drops. But what it does not do, it does not consider like interplay of multiple features that contribute to the prediction performance. So like the conclusion cannot be that, okay, we only take these 7 features and then we still get the same good prediction performance, because there is definitely some information in the other features as well. And this is what we showed with these categories of features, where we looked at different types of categories. And here we showed that the only one that was statistically significant, and actually by quite a huge drop in prediction performance, is all the features related to the code that the benchmark calls is relevant, or is like a good proxy for the variability of the individual benchmark.
Okay. Yeah, actually,
Thank you.
I was almost going to ask exactly the same question, but in that case, I have a follow-up question. So I assume your benchmark does not contain invocation of like I/O APIs or connection to network or databases, things like that, because those will likely be the most important sources of variability. That's at least what I would have expected.
Right, and this is exactly also the reasoning or the idea that we had in the beginning, and we actually included calls to I/O, to network, to all kinds of non-deterministic calls that could serve like as a proxy, because in the end we are just like, because we do static call graphs, we do AST parsing, so we only look at the source code. So in the end, we only have like an approximation of some dynamic behavior, which is the variability. And obviously, I/O, etc., is like a good idea, and we looked for that, and in our results, we do not find them to be most important.
Okay, thank you. More questions? Other questions?
I would have maybe a question for Daria.
Mm-hmm.
So what I find your study very interesting, because it's always like a debate of or there are, let's say, different school of thoughts of what academia in terms of education should provide. And my question to you would be, do you think academia should actually train students for the job afterwards, or like on the other side, give like a more theoretical, broad view on the field itself?
That's a very good question, and we discussed that a lot, both when I did my PhD at the university and afterwards with my colleagues in the industry. And my personal opinion is that we, of course, must provide the basic understanding of things like, for example, in our case, conceptual data modeling, but we cannot teach students without practical implementation. It's not possible to make it meaningful for the students without explaining them why exactly they need this knowledge. And I think that's the biggest problem in academia now regarding the software engineering education, because it's often that the students just don't understand, okay, why would we need okay, we learn this huge course, let's say on machine learning, or data mining, and it's very beautiful that we have this, I don't know, Netflix data or something. And but what do we do with it in the future? How do we implement it in our profession if we don't stay in academia? So that's, I think, that is the most important thing. I think, if you remember Richard Feynman, who gave the physics lectures, he would always provide the practical example. He would always provide, after each example of the physics law, he would always provide a practical example. So that's what we need to do. That's my opinion.
Okay. I have some follow-up also for Daria. Well, first of all, thank you very much for the great paper. I think I'm going to pass your paper right after this session to my colleagues teaching modeling at undergrad level, because the concept that you highlighted are so important. And in some sense, I would say shocking, but it's a matter of fact. Basically, I've seen this happening in the past, like people in industry I discussed it with, and they were just complaining that their junior developers did not understood such basic concept that should just come from conceptual things. So one question is whether you found differences between developers having a different level of experience or coming from completely different background on that, from the industrial perspective. And then, of course, I have a follow-up question as well.
Yeah. So sorry. Could you specify what?
Yeah. So the idea is that, assuming you have multiple developers coming from different schools or coming from both a master or undergrad curricula, did you find a huge difference between groups of industrial developers related to that?
We did not explore it specified to that because we don't have this data. Because we cannot collect data from our partners who come to the training. But overall, of course, it depends. Mostly it depends on experience. So people who have a lot of experience in requirements engineering, they naturally have this knowledge of through experience. But that's something that we need to explore. Okay. We explored it on the level of university students. So depending on which bachelor's they finished, they had different results in their conceptual data modeling course. That's for sure.
Okay. The other thing is whether you found difficulties related to domain-specific modeling, in the sense that what normally happens when you study modeling at school, you mostly model very simple and, let's say, repetitive domains, from hospitals to flowers and similar. But then you have to build a very complex model in the automotive or aerospace or whatsoever domain, and there things become more difficult. So I was wondering whether, other than those very simple and shocking mistakes related to cardinality and so on, you also experienced difficulties related to scaling up to very complex domains for what concerns modeling.
Yeah, that's indeed an issue. But what we have, particularly in these two courses that we explored in the industry and in the academia, they are very similar in terms of their context. So they are really not super complex, because we were working with digital asset management systems. So it's not rocket science, basically. So it's and we have very similar tasks also at the university. So, and still the mistakes were the same even with the professionals. So yeah, that's
okay. So one thing would be to provide in both cases a better case study for the students, so they can get practice on let's say non-trivial modeling problems.
Yeah,
Okay.
we do that as well, but as a let's say semester-long project. They have a semester-long project in a group, and there they have a huge requirements document with lots of different. Yeah, we have a model with 25 different classes, so that's quite a big one.
Okay. Thanks a lot. Other questions? No, not yet. Okay. Maybe I have one question for Wei. My question is whether your work is dependent or independent on the dependency installation environment, like PEEP versus Conda or the dependency management facilities.
Sorry, can you repeat the question?
Yes. So whether your approach is dependent or independent of the specific dependency management infrastructure, like PEEP versus Conda. Let me also write.
Oh, sorry.
No.
Okay. I see the question. No, our approach only work with the pipe.
Okay. So maybe
the knowledge
yeah.
from the PyPI. Okay.
Okay. Thank you. And well, a more perspective question. I don't know if you think about that. Before Christoph was talking about Go, how would it be possible to generalize your approach to make it workable, to make it applicable to other languages?
Yes, I think our approach can be used to other programming languages that has the transitive dependencies.
Okay. Thank you.
I want to climb the question by labor. I think the strength of the version selection is decided by the purpose of code reuse. If you are just if you are just reproducing the code, the minimal version is a better choice. But if you are integrating the code to the existing project, the newer version is better, I think.
Okay. Thank you. Then there is actually another thing that I wanted to discuss with you because it's an experience we made a couple of years ago with dependencies in continuous integration. When you have a project may have at least two types of dependencies. Let's make it very simple. On the one hand, you have the dependencies for the production code. On the other hand, you have process-related dependencies. So dependencies related to the build automation, to the testing environment, to the deployment environment. And depending on whether the dependencies belong to the production code or to the development environment, developers may make different decisions with respect to wanting to upgrade or not dependencies to the very last version. So what we found is that in many projects for production-related code, developers in many cases prefer to keep exactly that version. They don't want always the last version because they're afraid to breaking APIs. Whereas if they have a dependency related to a tool that they need to run, like a static analysis tool or a testing library, they say, okay, sure, please use the very last dependency, the latest dependency, because maybe it's the best one, it's the most updated, maybe for checking vulnerabilities or for checking bugs and so on. So what's your opinion on that? So do you think we should distinguish dependency management between production code and non-production code?
Our approach infer the environment based on a clean environment right now, but we think we should add initial environment for the integration or anything else.
Mm-hmm.
To start the dependency solving.
Okay, thank you. More questions? Okay.
There is a question in the chat.
Yes, you can speak.
Yeah, I'll read it for you.
Yeah.
Christoph asks Peter, the question is, do empirical results exist of a real-world transaction chains? If yes, how long are those, and what would be an acceptable duration for these chains to finish?
Yeah, so the length of these chains, so we work with real-world data. We actually reprocessed historical transactions, generated some storage access traces, and then use these for our evaluations. And the length of these chains depends. Like if we use one block as the unit of execution, usually one block can have up at most 200 transactions on Ethereum. So then, actually, in that case, it's often the case that one large transaction dominates the execution time, or just a few. But this is not very useful for parallel execution. So we actually chose a batch of blocks as the unit of execution, because then we have more room to work with. And well, we found many examples. We found, for instance, 10 transactions forming a relatively expensive chain, because each transaction was expensive and also relying on each other. But the other example that I mentioned, token transfers, are relatively cheap, where you could have maybe 100 conflicting token transfers in one execution unit. So the length of these chains could vary a lot, and the complexity could vary a lot too. In terms of the duration, I'm not sure it's yeah, so in our evaluation, because the duration really depends on your actual setup, it's not a very not a thing that's very easy to capture. So we used something unique to blockchain as a proxy for this, called the gas price, because on blockchains, for each step of execution, you have to pay a certain amount of tokens, and this is roughly proportional to the execution time. So in terms of the time, I cannot give you like a good answer, but usually I think if you execute a block, usually it wouldn't take more than a minute or so.
Okay, thank you. More questions?
I have a question for Daria. So from your presentation, we've learned that students and professionals are making same type of mistakes in terms of data modeling. So my question is, do you have any insights of the cause of these mistakes from both sides? Thank you.
Yeah, the place where things go wrong is translation from textual requirements so basically going from non-formal to formal language. So this is the place where it goes wrong, and I think that we all have bias regarding particular contexts, and we assume things. So people, instead of reading the requirements and assuming that we have certain vague spaces where we should ask additional questions from the customer, for example, they assume, and then this assumption leads to mistakes, because this assumption is not necessarily true, because there are places where you simply don't know, for example, which multiplicity there will be, and and especially many people would would make an assumption that something is more restrictive, so that it will be one-to-one rather than let's say one-to-many. Yeah, and so it's our inner bias, and it's typical for all people. It doesn't matter whether you are a student or a professional. It's something that it's the place where you need to ask additional questions, and people should learn that they must ask additional questions.
Okay, thank you very much for the answer.
Okay, I also have another question for Daria, because you were talking about formalization. Okay, in many domains, it's not just sufficient to specify models with association and cardinalities, but also specify formal constraints over the models, for example, using OCL or any other languages. Did you find the differences between industry and academia, difficulties on both sides and similar?
In our case, we did not have exact match between the two platforms that we used on that matter. They all experience different difficulties with that. So I think that's quite common. But this is not the core error that we experience. So if you in the paper that we have here at ICSE, there is also a link to my earlier paper about errors in modeling, and there you can see the statistics of errors that we get. So there we don't have actually much constraints errors. Most of them are more basic. They are related to multiplicity and like direction of association, etc.
Okay, thank you very much.
Welcome.
Other questions?
Yeah, maybe I can, also for Daria. So I'm wondering what could be a cause why both academics as well as industrial practitioners struggle so much with modeling. So, I mean, I would have a guess that, at least from my experience from the students that I taught, is that they might want to get their hands dirty as soon as possible and do not care about the earlier parts of the requirement stage. But maybe you have a bit more of like an elaborate answer to this.
Several years ago, it was I think 5 years ago already, we explored the most popular literature, study literature on data modeling, and we found that most of the literature does not provide any procedural knowledge whatsoever. So you don't there are no checklists, there are no like step-by-steps what you do, like which questions you ask, or what you explore first in the requirements, how you formalize. So these procedures are missing from all the, we explored the textbooks, we explored the massive open online courses, we explored the university courses. They are lacking. So the procedural knowledge is not there. And I think that's the place where it starts from. People simply don't have the procedure in their head, the protocol to follow. And because of that, they indeed jump to practice right away unprepared, and they don't follow the correct steps. So I think that's the issue.
Okay. Thank you very much.
I have another question to Christoph, if we still have time.
Yes, please.
So, assuming I have a project with micro benchmarks, assuming I wanna use your solution, how would that work? Like, would I need to retrain it with every commit? Would I need to rerun the benchmarks with every commit, or maybe daily? And also, what's the overhead? Like, how much does it take to evaluate these tests?
So yes, I definitely there is some effort that you would need to do. So one, we tried it on Go. So I think, like, at least conceptually, the features would also work in different languages, but yeah, tooling is missing for that. So this is one side. Then you would need to train your model based on your own environment where you execute the benchmarks in. So because, like, different, I don't know, let's say my computer has a different impact on the results as I don't know, like compared to another server or to a cloud machine. So you definitely need to train in the environment, or you would need to get executions that you can train the model on from the environment where you want to have the predictions for. Yes, so this is that. And then in terms of retraining, that I cannot give you an answer to that. So I don't know how often you would need to retrain. It probably depends on the stability of your environment over a duration of time, let's say. So if you are in the cloud, then which is known to have fluctuations throughout the year and with increasing, like, updates to the machines, then probably more often. If you have a very controlled environment where you do not update the hardware as well as the software, maybe less often. But it's a very vague answer that I can only give you.
I was actually thinking more of the evolution of the code. So not the environment, but how the code changes that might also change the results. But I guess the answer is it depends.
So, like, well, the evolution, so I can at least colloquially, we know that the benchmarks themselves, so the benchmark code themselves does not evolve much over time. But what definitely evolves is the code that the benchmark calls. But in terms of evolution, we are not looking at diffs of the features, but we are looking at the snapshot of every version. And my hunch would be that what affects the variability of performance is less dependent, or is less fluctuates less with changing code. But this is just a hunch.
Thanks a lot.
I guess we still have time for one more quick question.
If we have questions, yes, sure. No, if not, okay, if there are no further questions, let's thank the speakers again. And this formally conclude this session. Thank you very much for the great work.
Yeah, thanks everyone.
Thank you.
Bye.
Bye.